So for kinetic energy, we need to be able to express the speed of the object at any particular displacement from here. So at the moment, we've got a great equation for what the displacement is in terms of time, sine omega t times the amplitude, and therefore that also gives us v equals a omega cos omega t because we'd differentiated it. So if we start with that we've got the speed of something travelling with simple harmonic motion is a omega cos of omega t, where the equation of the displacement is a sine omega t, because that starts from 0 at time equals 0. We're going to be using the trig identity sine squared theta plus cos squared theta equals 1 that you should know from your maths. If we square that equation for speed, v squared equals a squared omega squared cos squared omega t, then the cos squared omega t, if we use the trig identity cos squared theta is 1 minus sine squared theta, we can say that v squared is equal to a squared omega squared cos squared is 1 minus sine squared omega t. And if we put the a squared inside the brackets, got omega squared a squared minus a squared sine squared omega t. Just to make it completely obvious, I'm going to rewrite that again. V squared equals omega squared a squared minus a sine omega t all squared. Hang on, a sine omega t, that's what y is. So we've got v squared equals omega squared a squared minus y squared. Now isn't that easier? So we've been able to use that trig identity to put the y displacement in instead of a time-dependent function. We will come back to that equation in just a moment, but if we take a square root of that, we've got v equals, remember square roots can be plus or minus, omega square root of a squared minus y squared, and that equation is given on the SQA formula sheet. The v squared is quite handy because what we started off with was wanting to know what the kinetic energy is, and kinetic energy of course is half mv squared, so we multiply that by half m and you get the kinetic energy is half m omega squared a squared minus y squared, and that's the equation for the kinetic energy of something moving with simple harmonic motion if you know the y as a variable. You'll notice that it's got a wonderful similarity with the potential energy equation, which was half m omega squared y squared. The two are quite complementary, and I'd like you to go back to those Desmos graphs to see which is which. If you plotted those two against a y displacement, what would the graphs be of potential energy and kinetic energy for amplitude amplitude A? So what would the shape of those two graphs be?